In this video, we're going to be talking about special systems. So we talked about solving systems of equations by graphing, by substitution, and by elimination. And one thing to say about special systems is every system that we talked about so far has had a solution. Like if we were looking at the graphs of a couple of linear equations, and you graphed them, they would have an intersection, and that was the solution. Now, for special systems, there are two cases. There are ones where there are going to be no solutions, and the graphs of the linear equations are going to be parallel. So this one has no solution. Notice how they don't intersect. Kind of like railroad tracks, they just go on forever and ever and don't touch each other. The other kind of system that we're going to talk about, one of the special systems, is one where there are infinitely many solutions. So we would have a graph and another one just right on top of it. So basically they make the same graph. They might be the same equation, they might look a little different, but they make the same graph. So here is a system with no solution. So we want to solve y equals x minus 1 and negative x plus y equals 2. So we want to see, like if we didn't know if there was a solution, we want to see if there was one. Let's take a look at a graph quick. Let me get a graph up there. So let's graph the first one, y equals x minus 1. So I have a y-intercept of negative 1. I have a slope of 1, so go up 1 over 1. And here is my graph for that one. Let's take a look at the next one. Let's get y by itself, so let's add x on both sides. So we get y equals x plus 2. So I'll graph that one in red. So y-intercept of 2, a slope of 1, so we go up 1 over 1. And there we have it. So we can see by the graphs that the system has no solution. Okay. Two things that I want to mention. The first thing that I want to mention is that systems with no solution have the same slope. So if you look at this equation, and compare the slopes, they both have a slope of 1. So systems with no solution will have the same slope, but a different y-intercept. Okay. So we could have actually not even graphed the thing and looked at the two equations and said, oh, well, since they have the same slope but different y-intercepts, it's going to have no solution. Okay. So we'll actually be doing some of this in the homework later. The second thing I want to note is, like, let's say you wanted to solve this system by substitution. You can use elimination if you wanted to. We actually graph the thing. But let me rewrite the system here. So we have y equals x minus 1 and the original negative x plus y equals 2. So remember, in substitution, I want to take one of them that is solved and plug them in for the other one. So let's plug in that x minus 1. Okay, so we got negative x plus x minus 1, plugging that in for y. That equals 2. And now you have a negative x and an x. So those are actually going to cancel out. And all you're left with is a negative 1 equals 2. Okay, well that is actually false. Okay, negative 1 does not equal 2. So this indicates that it is no solution. So going through the homework, you're going to say, determine if the system has no solution or infinitely many. You can look at the slopes and the y-intercepts, or you can look at it algebraically here. So we'll get into a problem like that a little bit later. Systems with infinitely many solutions. So let's take a look at this one. Let me get a graph on there. So we have y equals 2x plus 1. Let's graph that. I have a y-intercept of 1, a slope of 2, so up 2 over 1. There we go. Looking at the next one, let's get that solved for y. So let's subtract 2x on both sides. So we have negative y plus 1 equals a negative 2x. I'm going to subtract 1 on both sides. So a negative y is going to equal negative 2x minus 1. And I want just a y. I want to get rid of that negative. So let's divide by negative 1 on both sides. So essentially what that's going to do is flip all of the signs. Now you notice how, oh, well, I have y equals 2x plus 1 again. So that's going to make the same exact graph. So that's what your graphs would look like with infinitely many solutions. It's going to make the same graph. So going back to two different things I wanted to show you. Step one, systems with infinitely many solutions have the same slope and the same y-intercept. And let's take a look at if I wanted to solve this one by substitution again. So another way of looking at it. So going back to the original, y equals 2x plus 1 and 2x minus y plus 1 equals 0. So let's say I wanted to solve that by substitution. So I would have to take the 2x plus 1 and plug that in for y. So I have 2x minus 2x plus 1 equals 0. Okay. Got to distribute that negative sign through. So I have 2x minus 1 plus 1 equals 0. Okay, so the 2x minus 2x is going to cancel out. Negative 1 plus 1 are also going to cancel out. So I have 0 equals 0. Now, whenever you have a number equals itself, that is true. And whenever you come across this situation, that's going to indicate that this has infinitely many solutions. So if you're solving this algebraically and you get the same numbers, it's going to be infinitely many solutions. Whereas the one previous, if you get two different numbers, it's going to be no solution. All right, so here we have a problem, and we need to determine if the system has infinitely many solutions or no solutions. So right away we know it's a special system. And there's going to be two different ways that you can do this. So the first method is to compare the slopes and the y-intercepts. And remember, if we have the same slope, the same y-intercept that had infinitely many, if we had same slope, different y-intercepts, so they'd just move up and down but be parallel, that would be no solution. So you want to solve for y when you do it this way. The first equation's already solved for y. We got y equals negative 2x plus 5, so it has a slope of negative 2, a y-intercept of 5. But let's get y by itself on the second equation. So we need to subtract, let me rewrite it over here. To get y by itself, subtract 2x on both sides. So we have y equals negative 2x plus 1. So we note that they have the same slope, but different y-intercepts. So if you graph the thing, and you don't need to graph it, but if you did, one of them would look something like this going through 1, and the other one would look like this going through 5. So this one actually has no solution because it has the same slope and different y-intercept. Now the second way that you could go about this is to solve the system algebraically. So let's say I wanted to do it by substitution, put that in for y. So we have 2x, and this is the algebraic way. 2x minus 2x plus 5, and that equals 1. So 2x minus 2x, those cancel out. I got 5 equals 1, which is false. So that as well indicates that it is no solution. So however you do it, if you want to do it the first method or the second method, you're going to get the same answer. So let's take a look at another one. Again, we have to determine if it is if it has no solution or infinitely many solutions. So the first way is to compare those slopes and y-intercepts. So the first one has a slope of 1 and a y-intercept of -3. And there's that invisible 1 there. The second equation, I have to get the y by itself. So x minus y minus 3 equals 0. Okay, let's get rid of that x by subtracting x. So that cancels out. -y minus 3 equals a -x. Continuing to get that y by itself, let's add 3 on both sides. So I have -y equals -x plus 3. I need to get rid of that negative, so let's divide by -1 on everything. So remember, dividing by -1 just flips all the signs. So I have y equals x minus 3. Okay, so if you look at these, they're the exact same equation. So this indicates that it has infinitely many. Solutions. Because it'll have, of course, the same slope and y-intercepts, because it's the same line. It makes the same graph. So let's take a look at the second way of doing it, the algebraic way. So let's say I wanted to substitute x minus 3 in for y in the other one. That means I would have an x minus 3, and then another minus 3 equals 0. So distributing the negative through, I got x minus x plus 3 minus 3 equals 0. Now the x and the minus x are going to cancel out. 3 minus 3 are also going to cancel out. So I just have a 0 on the left side. That equals 0 on the right side. And that, of course, also indicates that there's infinitely many. So whatever method you want to use, whatever one you like to use or you're most comfortable with, go ahead and use. But either way, it's going to give you the same answer. So taking a look at a couple word problems. So Matt has $100 in a checking account and deposits $20 per month. Okay, Ben has $80 in a checking account and deposits $30 per month. So will the accounts ever have the same balance? Explain. So you're going to have to use your brain on this one. And there's actually multiple ways that you can look at this. One way you could look at it was make a table. Okay, well here's Matt, and here's Ben. So at the start, Matt has 100, Ben has 80. Okay, after 1 month, since Matt deposits $20 per month, he'll have 120. And since Ben deposits $30 per month, he'll have 110. After 2 months, Matt's going to have 140. And Ben's going to have 140. So will the accounts ever have the same balance? Boom, yeah, right there. After 2 months, they have the same balance. So this really all depends on how fast somebody is depositing money. Since Matt is putting less per month than Ben, eventually, yeah, Ben is going to have more money than Matt. You can also look at, since we're on the topic of systems of linear equations, a graph of this. So let's make this 100, here's 50, here's 150 or something. After month 1, 2, 3. So if you look at Matt's, he started at $100 and he deposits $20 per month. So we'll have a point at 1, 120. And then 2, 140. So here's his linear graph. And then for Ben, he starts off at 80, but he puts $30 in there per month. So after 1, he'll have 110. And then after 2, he'll have 140. So his graph looks something like that. Not perfect, but... and it all depends on how fast or what the rate of change is. So looking at the 20 and the 30. So let's take a look at another word problem. We have Mika runs on a treadmill at 4 miles per hour. He has walked 2 miles. When Luke starts running at 6 miles per hour on the treadmill next to him. So if their rates continue, will Luke's distance ever equal Mika's distance? Explain. So it's like I said, Mika is walking at a slower rate than Luke. Okay. So eventually Luke is going to catch up because, yeah, and it doesn't matter how long it is, but he will actually catch up if he can run as long as he can. It does, the question doesn't really ask that. And you could look at a linear graph of that as well and compare the graphs. So we have Mika at 4 miles an hour when he's walked 2 miles. So here's 2, 4, 6, 8. So we'll go after 1 hour, 2 hours, 3 hours. So he's at 2 miles. And then after an hour, since he's running 4 miles an hour, he'll get up to 6. And then he'll get up to, adding another 4 to 10. And it kind of goes off my graph here. Oops. Let me move this down a little bit. There's 10. So after 2 hours, he's going to run 10 miles. So here's his line right here. But then when Luke starts running at 6 miles per hour on the treadmill, so he starts at a distance of 0, and then he's running 6 miles an hour. So after 1 hour, he goes 6 miles. So actually, even after that 1 hour, he catches up with Mika. So however you want to word it, what I want to see is the rate that one person is going is faster than the other person. So that's the main idea behind these word problems.